Hello everyone. Thank you so much for staying. So my name is Miloš Rankovič. Even though the name sounds Czech, I'm not Czech. I'm from Serbia. So I did my PhD in Serbia in 2016 in physics, and now I'm here working as a postdoctoral researcher in the Jaroslav Herovski Institute of Physical Chemistry, and I'm also doing very similar stuff as what Tom is doing, electron collision stuff. But since he already gave this talk, I figure I'll pick something else, which I'm personally interested like as more as a hobby. So what I will be talking about today is not what I work. So what I do is what Tom do. But this is what is really interesting for me. Except for this, of course, there is. In science, it's difficult unless you're working on something really like top-level science. This would be super interesting. Everything else is more or less hard work. So you just dig in, you do a lot of stuff, then you get some results, you publish it. There's nothing exciting, You see some graphs. It is exciting for us because we are interested in a fundamental physics. So what on a molecular level happens there, but how, if this contributes to the mankind, who knows, maybe. You do small steps and then see what happens. Okay, so today I'll be talking about machine learning. So this is a pretty popular topic now, especially in these years. So, and this has grown a lot, and it's already spreading in our lives. So in our daily lives, we are, without even knowing, it's already there. So this is just a short outline. So I will just explain what machine learning is. So if you have never heard about it, I will talk about some types of machine learning that exist and some models that are in there. Also, I will focus mostly on the neural networks. I'll talk afterwards, in more details. I'm just now laying out the layout. And also, I will be showing one particular application of the machine learning on a PC game which I developed. Actually, when I came here, as a new guy in a new city, you don't know many people, you have a lot of free time. So I figured, okay, let's do a little bit of programming. I was getting a little bit better, and then I made a game, and then a few years after, so I figured, okay, let's try. I was watching on YouTube some video clips about machine learning, and the guys making these artificial intelligence stuff. And I was like, okay, let's give it a try. Can I make like artificial intelligence that will play my game? Like learn itself how to play it, and then maybe show me some new stuff that I didn't know that there are in the game. So the game looks something like this. This is just a teaser. So afterwards I will explain more about it. So what is machine learning? Some smart guy once said that it gives computers the ability to learn without explicitly being programmed. So what does that mean? So sometimes you have a problem which you cannot just solve by saying, okay, let's make algorithm. If this condition is satisfied, we do this. If it's not, we do other thing. And then make some structural way of questions, okay, and go here, go there. So it's not possible to do. So there is actually where machine learning comes into. So this is what I just said. So it creates certain types. These are still algorithms, but not in a direct way made that they solve the problem. It's a little bit indirect. And of course, to do this, you create some kind of model which will suit to different problems, and then try to solve the problem. And some examples, like for example, problem which you cannot solve by algorithm, like a spam filter. So how do you, for email, so you receive some emails, how do you know which email is a spam? There's no way you can make some questionnaire or some algorithm which will know which email is a spam. But implementing machine learning, you can find actually what is a spam, and so on. Of course, object recognition. For example, you give a picture. For us, what it seems so easy, like you see an apple on a picture, you can right away say this is an apple. But for computer, picture is just numbers, so it doesn't know what apple is. And it would be extremely difficult just to program to make a picture of any apple and then the computer guesses that this is apple. This is extremely difficult, but this is also where machine learning comes to play. There are different types, of course, different problems. You need certain approaches. So three main types of machine learning. The first one is the So three main types is unsupervised learning, supervised, and reinforcement learning. So what does those mean? Unsupervised learning is where you don't need to involve. So you make your algorithm, and then this algorithm tries to find some patterns in your data which you put in, and then this you can use, for example, a recommender system. So when you surf your internet and then you see like a pop-up, some commercial, which gives you some recommendation based on what you were searching previously. So that kind of algorithm already looks what you did before, and from that learns what you might want to look again, and so on and so on. The other type, the supervised learning, is when you need to involve. So you need to tell the computer, you show him an apple and tell him this is an apple. You show him an orange and tell him this is an orange. And then you try to teach the computer to recognize what is what. So this would be supervised learning. And the other type is reinforcement learning, where you actively say, computer, do something, and then he does something. And if he does something which you like, you say, nice, great computer, so do this. You reward it. If he does something stupid, you say, stupid computer, don't ever do this. And then you go on. And today, for this particular problem game, I'll be using and focusing on this reinforcement learning models and types for the machine learning. And there, finally, we come to the neural networks. So in this type of modeling for machine learning, you would implement neural networks. For these other ones, you would use some different models. Because I made this game and implemented this, I know how this works. So these other ones, I don't know. So this is, entire field of science is there, and people are working on each of those. So those are like very specialized, very, very difficult stuff, which I don't know much about, but I can talk about this one. Okay, so let's go on to neural networks. In the simplest way, neural networks is just a mathematical algorithm, and you use it to solve some complex problems. So important words which will show up are neurons, weights, biases, and activation functions. So I will talk about each of these separately, but here I drew just like a simple representation of a neural network. So how we usually want to see something. So this is just a made-up thing, but representation is a way to just make it somehow that it looks like somehow that you are easier to interpret and easier to see that thing. Okay, so let's start. Let's say we have a neural network which consists of 4 neurons. So here, A, B, X, and Y would be neurons. These are numbers, let's say from some negative numbers through 0 to some positive numbers, doesn't matter. So here we would have some input and output neurons. So we would start, if we have a picture with an apple, input neurons could be values of pixels, of each pixels on that image. And the output neurons would tell, for example, X1, X would be apple, this one would be orange. Then if we get like 1 on this one, this would tell that it's apple. If it's 0 here and 1 here, this will say it's an orange. So in the most simple way, you can do different stuff. It doesn't matter. It could be also numbers and so on. Okay. Those neurons are connected in some way, and so they're connected with weights. What weight is also another number, which just says this neuron is connected to this neuron with another number. I'll show in a mathematical sense how this is connected, but basically each neuron is connected to each other. And to make things easier, I just marked or labeled each of these weights. Okay, so now unfortunately I have to do some math. I tried not to put any equations, but I guess everyone can understand this, just addition and multiplication. So the value of neuron X, you would simply calculate by all the neurons which are connected to it. So to the neuron X is connected neuron A through this weight, and this neuron B through this weight. And it's simple as that. A times this weight plus B times this weight. And that's it. And the same goes, of course, for the Y neuron. So that's as simple as that. It's one neural network which has two inputs, 2 neurons on the input, 2 neurons on the output, and that's it. Of course, if you want to make things a little bit more general, then we would introduce a bias. Bias is just another number which slightly offsets these values. So it gives you ability to just push it a little bit up or a little bit down. As another number, so you just add it at the end. And luckily for us, there is already in the mathematics a procedure to deal with this kind of stuff, and it's called matrices or matrix operation. So here is how we would write these two equations in a matrix form. And now we would deal with matrix, weight matrix, which is this one, and the biases matrix, which would be this one. So these are essentially, you can see it as a vector, just a coordinate of in this case two numbers. So like x and y coordinate. So this would be the output neurons, and A and B would be the input neurons. And what is important for this particular neural network would be these two matrices. So the weights matrix and the bias matrix. Okay. So just one more step. Activation function. So what I just said before, we would do that way, but just additional. We would take a function of that equation. We just take one more function of that, and then we're done. And usually, you can have, depending on which problem you want to solve, you would use different types of functions. For example, this can be like threshold function, which is like a simple function. If number is below this, nothing. If it's above, you would give it another number. And ramp function, or which is most used, is this kind of sigmoid function. So I show a graph how it looks like. So basically, this function just limits the values. If you have inputs from like -infinity to +infinity, this function would limit those numbers from 0 to 1. Just like compress the values, so it's much easier to work with. And if you follow the same form, then it's just basically like this. So the same matrix as before, just to calculate the final neurons, you just take the function of whatever here was. Okay, so in principle, that's all the mathematics about the neural networks there is. I hope it was not too complicated, and those will be, if I'm not mistaken, the only equations that I had so far. Okay. So the procedure which I just described enables you from some inputs calculate the outputs, and this is called forward propagation. There is also another way to do it, so which is called backwards propagation, and this is if you already know what the outputs should be. So this is the case if you have a picture of an apple, you already know that output should be, you know, the one that will show the apple actually. And then from there, you can calculate what your neural networks does. You see the difference, and from that difference you go on backwards and calculate and get the right weights and biases. So another very important thing is training. So what training of neural network is, means you need to find all those weights and biases. So basically the entire problem goes down to find these particular numbers. You would start with some random values, and for certain problem those values will be in some small ranges and you have to find them. And then whatever apple you show, it should always, you know, guess that this is an apple. Okay. So about the game. So this is, as you could see, looks like a spaceship with some obstacles in most simple way. I used the programming environment called processing. This I have the, if someone is interested, so you can check it out. This is free and open source. So there are many libraries, and it's Java based, but it's also similar to C++. And so basically I knew nothing about it when I started doing this. So maybe I started in 2016, and you know, by this time I was able to, you know, to make something like this, as you will see. The game rules are just simple, just stay alive as long as you can. Okay, so now more about the game. So there is a ship which you can control. There are some ship can move up, down, sideways, left, right, and also it can rotate. And there is another control, like a fourth control, which is a fire button, so you can like fire a bullet. And there are some objects, some different objects, which if you shoot or if you collide with, some different outcomes will happen. Okay, and now at this point I can show you how it looks like in a real time. So I will try to play it. So as I said, so you can go up, down, you can go sideways, or you can rotate. And then of course you can fire a bullet. So now I will just kill myself by doing this. Maybe another try. Okay. So this was just to show you how the movement is done, and now I will restart and start actually the game. I'll try to play the game. So this is what I would do. So I would shoot this one, maybe turn on the sound. It's more interesting. So ship has a size which is defined by the health. So the less health or the size you have, you are smaller, and then you're lighter, so it's much easier to move, or you're more faster, so it actually makes it more difficult. But if you take a green one, this gives the health to you, and so on and so forth. Okay. So this is basically the game. Okay, let's go back to the presentation. Okay, so now how the machine learning or artificial intelligence, how would play this game? What would it do? What's the approach? So as I said, reinforcement learning would be the model of the machine learning. That would be the type, but in essential, we would use neural networks and genetic algorithm. Okay, so what is genetic algorithm? Usually you observe nature and use what is already happening in nature. So the principle of this genetic algorithm comes down to the survival of the fittest, exactly like in nature. So you would start off with some population. You will have, I don't know, hundreds of individuals, each of them will have some behavior, then they do something. At the end, only one survives, or only one is the best. So that one, you call it fittest or the best. He gets to reproduce. He makes another, let's say 100 individuals. And then what is essential to evolution is mutation. So each of these individuals will receive a small change of the behavior, such small mutation. And then you go back to the beginning, you get a new population, and then they again start the same process again. So this entire process you call a generation. And this is how this machine learning or artificial intelligence would play the game, through generations. You will start with the first generation, they do something, the best one survives, you take its neural network, mutate it a little bit, start a new one, and then so on and so forth. Okay, so now let's see how this AI deals with the game. I will say let's say a population have 256 ships. There's also a two-player mode. If someone wants after to challenge me, you can. Okay. So how would you teach, let's say, a baby what apple is? So you would show an apple and you say this is an apple, and then you show a different apple, this is an apple, and so on and so on. You would start with the simple things. Of course, you cannot. If you want to teach a baby to speak, there's no way it will tell a word. You have to start with the small things like daddy, mommy, and so on. Here I'm starting with simple things. So maybe this is even too complicated, but I thought it's simple. So what I do, I cluster different objects. So the red ones here, green ones, these are like immortality. If you take this one, then you're immortal for a second. This one is like a super bullet, which goes super quickly. So what I'm doing here, I'm teaching them it's good to take the green one, it's bad to take the red one, it's okay to take just the gray, and so on and so forth. And also, what I'm teaching to them is it's bad if you leave the screen. I don't want them to have a crazy speed, like just flying through the air all the time. This is, what I was doing. I was always trying to stay stable and try to control my. So this is the reinforcement part. So if they leave the screen, I reduce their health. If they shoot the red one, I increase their health. So these are not the default game rules, but I would do this to encourage them to do what I think they should be doing to do good in the game. This goes like that. This is a training process. So they start doing absolutely random things, and already, so now we don't see it from the reflector. It's generation 7. So generation 7 already learned. So let's try to stay in the screen. They were at the beginning just going all the way. Already by the generation 7, they learned that it's good to like try to only move slowly. So essentially that's it. So now I was showing all 4. I'm now trying to teach them what to do with the green ones. Then it will come the blue ones, and so on, and generations and generations. So this will go for a very long time before anything interesting happens. So I'll just skip forward to it and show you what is the outcome, which probably would occur to any of you to do this, and try to play the game that way. But let's see if you guessed it, what it was. So you come to something like this. So this is after 12,000 generations. So because the training goes in real time, what I do every time I come to my work, I start the simulation, I let them train, and I also made it a way how to save it. So every day, if I see this one is doing good, I save it. And then next day load it and start again. So this was, I think, months, months of training. It does go that, like, I think after millions of generations, we would see even something more spectacular. But this guy, ship number 236 out of 256 that are in population, he realized this is actually a smart guy, because the more stupid one just stayed where he spawned, where he was created, and was just spinning and shooting. So because in the game, the rules are, I just spawn randomly those items, but if it spawns where the ship is, I don't show it. So he realized if I stay in place, nothing will be created where I am, and basically I just rotate and shoot, and that's how he survives. So basically this is what they learned after 12,000 generations, or much more than 12,000. I run it maybe 20,000 the next day or next month, and so on and so forth. So this would be what I prepared for you. Thank you very much for your attention. Let's go back and see how they're doing. So I will load this smart generation. So I'll press L and load this like months of training, and then see. Basically the same would be happening. If you want to see the picture which I just showed you, this would take, I don't know, maybe 10 minutes or 15 minutes, but it doesn't matter. I'll just leave you with this like super trained, but they are still stupid. I mean, it's, if you think about like a scenario of Judgment Day, like Terminator taking over, just look at this, it's so difficult to train anything. And this is extremely simple case, You have a self-driving car which needs to scan the environment, and this already very complicated problem, let alone like to rule the mankind, and so on and so forth. We might see, I think, the machine learning in like this, what offers you as a commercial, what you would want maybe to buy, and so on. This would be this is already now in our lives, but this, I think, would be the future. It would be rather helping us than taking over us. But yeah, I don't know. Who knows? It's a big discussion.
So, questions?
Sure.
Can we play it somewhere?
Well, I didn't publish it anywhere online, but we can play it here. We can have like 2-player battle.
How soon would you expect that they would behave like you would do?
Yeah, this is
Hundreds of years.
No. I think it's just down to what kind of rules do I put on it? What reinforcement I do? So what I did is I told them if you spin too fast, it's bad. If you leave the screen, it's bad. And what else did I put? Maybe I put too few rules which will tell them don't do this, and it's already too complicated. Even for any of you, if you start playing, you would see red color, green color, yellow. What is this? It's difficult once you hang on. First, it's difficult to control it. I also implemented friction, so it's much easier. So without friction, as soon as you press a control, the ship goes on forever, just because there is no friction. So with this rate, it's a bad implementation to learn because it's doing in real time. And this is what makes it slow. If I wouldn't show the graphics, it would run much faster. But I didn't do this. This is so far where I got. If you would implement everything correctly, I think this would be, you would be able to train it within weeks, and it would be a much better player than any of us could be. But I was not able to train it. At this stage, I'm training it to play the game. the next step would be train it to play against me. This is what I wanted. Like usually when you have the games, you play against the computer, and then you play against the computer. So, but rarely any game has a neural network implemented in there. It's usually set of rules, explicitly programmed rules how the thing behaves. No game has the neural network implemented in the. But you can do it. I don't know. Maybe they're doing it. I think one game called Overwatch, they even implemented a thing where the bot or AI would watch a human player, and when it sees a human player does something, it will try to do that, and then it will teach a new human players that come. So it is also happening. But long time. Like this, it would take very long.
Have you thought about different approach? So instead of reinforcement, try a different type of AI?
Try to what?
Try a different type of AI?
No, because you would different types are not for this type of problem. So different types are classification and finding some patterns and so on, which are suitable to recognition of Apple, what I just said. But for this type, you would need a reinforcement model with neural networks. There are some other, I think, approaches except for neural networks, but I wouldn't know. I'm not an expert in that. But for this particular, neural networks are the most spread method, so you would use that. What I didn't mention, neural network of the ship or the brain of this. Each ship has its own brain, which is individual. And here, I'm actually representing or showing you the brain. And you can see how it thinks. Yeah, I didn't talk about this. Maybe I should mention. So the blue ship is the one that is currently the best one. And its brain or its neural network is presented here. So this is the input. And this is the output. So there are 4 outputs, controls. Up, down, this would be like one axis, one control. Left, right is this second neuron. Rotation and like shooting the gun, this would be the 4th. And the inputs are here. So if I press T, this is like a vision. This is how I give the ship ability to see the world around itself. So these are rays, which I can adjust. For now, I just put that he sees all around himself, but there's only 9 rays. I could make them just straight and put 10 or 20 or so. These are all things when you ask how long it takes to train. If you change these things, this would change. So there's always a balance. How big a neural network you want to make. If it's bigger, it would be able to do more complex stuff, but it'll take a longer time to train. So you need to find the balance. What are the essential details that the ship needs? So I was thinking the way I played it. How do I play the game? So I see what is around me, what is nearest. So the ship is able to detect the distance of the object. So if the ray crosses any of the object, the ray then becomes this color, and then it gives the distance. And so those would be the inputs. So the first this inputs would be just from the vision. So the next ones would be the ship's speed, coordinates, how much health it has, how much bullet velocity. So basically all the information the ship has are the inputs. And then what it does is just adjusting this, or basically I'm selecting always the best one. And all these weights are just at the beginning random, completely random. The ship just flies away. He will not be rewarded. But ship that stayed, he had such weights that made him that, it was not pressing too crazily the button, so he stayed. And these weights were good. So this brain or this neural network was good. So he would continue. And reproduce, of course, and then each one of them, I would mutate a little bit, and so on and so on.
Do you somehow work also with the psychology and with the knowledge which is based from there? And also, what do you think should be the role of ethics in machine learning? Because, for example, when Amazon wanted to do the unbiased recruiting system, historical data which were sexist, the machine turned to be super sexist, or when they were trying to program some security system, historically there was discrimination, so it turned out to be very discriminative and racist. So what do you think should be the role of that, and did you use some knowledge of psychology?
No. But there is definitely, you can implement neural networks also in such a complex situation like human behavior. So this would be definitely out of my reach, what I know about machine learning. So I cannot really comment on that with you know. There is definitely ethics, you know, you have to think about this, but I'm simply not able to. I'm not able to tell you. Yeah?
If I remember that correctly, you work in this same more or less field as previous speaker.
Exactly, yes.
Did you consider using such kind of methods to modeling what actually happens with electrons?
Yes. So, yeah, to answer the question that he got, so this type of simulations that we do, or these modelings, are very simple. So you're not simulating what happens in experiment. You're just modeling a molecule and then trying to see one property of this molecule. We're not doing any simulation which involves like electron goes in and then there's interaction, there's ionization. We're not doing those kind of simulations, but there are groups that do. We collaborate with one. There are, of course, theoreticians. They do such kind of simulations, and they did try to implement a neural network. So, for example, think about this. You have a certain problem, electron hits a molecule and so on. You create some model which describes this thing, and what you do in physics usually is parameterize the thing. So make like, I don't know, 10 or 100 parameters which you can fine tune to get to replicate the results from the experiment. This is how the modeling works. Actually, the theorists on them alone are not able to do much. For a simple molecule like, I don't know, hydrogen or nitrogen, 2-atom molecule, they can do wonders. But as soon as you add 3 atoms in a molecule, 4, 5, you know, anything else, it's like science fiction for them. So this is extremely difficult to do, like exact calculations. You don't usually do things. But what I wanted to say, if you make 100 parameters, then you can use neural networks that will find, so you can think about those parameters as the weights. So as these things in here. Here is your experiment, some results. Here are some inputs. And then you try to optimize, this is called back propagation. You can try to find your parameters which would then fit with the experiment. This way you would implement machine learning into your code. So your machine learning will find you the optimal parameters which when you put in your simulations for a certain input recreate the good results which we see in the experiment. So in that way you would implement, but they did try a little bit. I don't know how far they did go, but still this is like only a few publications are, I mean, of course many publications are all over around the world, but I don't think they did any real breakthrough. It's really difficult. You know, once you have enough complex simulation to describe the experiment, you get thousands, I don't know, maybe even millions of parameters, and then it's a real difficulty to train. How to train or how to optimize, you know, which model to use from the machine learning to find all those parameters.
So, and here we are running out of time, so let's thank Miloš.